A word of warning to those of you that are sitting in the back 3 or 4 rows. We had a student, those of you that were here Tuesday, remember I had to call a student up to the front because their clicker was not clicking. It wasn't even connecting. She was way in the back, but by the time she got up here to the front, it was working really well, And so what my fear is that you guys in the back 3 or 4 rows, it's possible if you get your nose out of your phone. Look at me and listen. If you're a little bit nervous about your clicking grade, it might be because your clicker's so far back, especially you guys back there, all the way back in the bad boy row. The bad boy row, that term was invented in this room a number of years ago for the guys that used to sit in the back all the way back over here. And they said, Dr. B, it's just like on the bus. All the bad boys sit in the back. And anyways, you guys in the bad boy row back there, and all the way in the corner, you might want to move forward, because if your clicker doesn't, put out enough energy, I might not be catching it. I'll give you a minute to change seats if you want. Go ahead and change seats. A few of you have already done that. Move forward. Nobody's moving forward. Well, it's your... No, don't move backwards. Okay. Don't deliberately sit back there. Anyways, it's your funeral. You do what you want to do. Yeah, the back row's open. Yeah, question. Then your SO, if your clicker's not clicking and, I'm not getting it, what am I supposed to do? I can't do anything. But, the thing is, most people that have been in that spot know about it and have already corrected it. The student that we called earlier, she had another problem. It wasn't because of that. We called her forward. She had another problem with her clicker, and we solved it. But if it's just like taking an online test in web courses. Do you know? Raise your hand if you're taking or have taken an online class in web course. That's a bunch of you. Did you know that they tell the instructors that if the student has a problem with the internet, like the internet service provider craps out, we're not supposed to help them? And the reason they tell us that is because it would drive us insane to try to troubleshoot people's internet service. Because, from my house and trying to figure out and you might live in Kissimmee or even, in the Philippine Islands. We've had online students in the Philippines before. So, that's what they tell us. Every instructor here goes through the same course to prepare them for teaching online, and that's one of the things that they tell you. Don't, so that's why I always tell my online students, be ultra paranoid about your internet service. And the same thing here. Be ultra paranoid. Now we know that you should be paranoid. And we do on exam days, I push all you guys up towards the front anyways, for other reasons, so it doesn't show up on exam days, but class days, it would explain a lot. There's been an awful lot of students that have had troubles with, Dr. B, where are all my clicks? Where are all my answers? And there's various reasons for them. I sure hate that it would be something like that, but apparently for some students it is. All right, let me also mention to you one more time, for those of you that were not here Tuesday last week, using someone else's clicker when they're not here, or even when they are here, that is cheating. And we have various ways to detect it. So if we decide that we're going to do that, and we've detected it with some other students in the morning lecture, so if that, I'm not looking at anybody, but if that describes you, don't do it. All right? And you know, there's not like, you know, I can mentally hypnotize you or detect your brain waves or anything. So if you decide, screw you, Dr. B, I'm going to still do it, I can't do anything about it, you know. But try to do what you think is right, and that would be the right thing, is to not do it. All right. Last time we talked about shock waves from core collapse supernova, slightly different from type 1a supernova. And I love this set of photos of Navy fighter jets. And what you're looking at there is a pair of jets just at the moment they break the sound barrier. And a shock wave forms. We hear it as a sonic boom. You know, like when the space shuttle used to come in for a landing, it had two sonic booms. I'll never forget the first time I heard that. And this is, you know, one size smaller aircraft. And what happens is a sonic boom is a shock wave. We would call it a shock wave. And it's a rapid pressurization and then decompression of the air. And when that reaches your ear drums, you hear it as a boom. Broad frequency, broad spectrum audio boom. And when you see it with fighter aircraft near sea level, if the air is humid, as it sometimes is by the sea level, or frequently is by sea level, it will cause a rapid pressurization, then depressurization, and that'll form droplets of water. And that's what you see. These little, you know, like this cone-shaped cloud appears to be cone-shaped over here on the right. And then this one's a little more nebulous, a little more formless. Those clouds that you see, those are micro droplets of water. That's what a cloud is. It's not water vapor, Sophia. It forms from water vapor, but it's actually small droplets of liquid water reflecting sunlight that rapidly get re-evaporated. Okay, so when the shock wave passes, they're small enough that they'll be rapidly evaporated back into the air. And if you ever go out west, you know, like to Montana or Arizona, sometimes you'll see thunderstorms, 40 miles away, out in the big wide open spaces. Or sometimes you'll see it if you're driving across the Everglades. You can see a long way down there. A lot of times you'll see a thunderstorm dropping rain down out of the cloud, but then it just kind of peters out, it disappears. Those raindrops have evaporated again. Sometimes you see it a lot out west. It's a little bit less frequent here in Florida, but you sometimes see that. That's what you see here. This shock wave forming the droplets forms this shiny white cloud behind the aircraft on the right, but the conditions are such that the droplets re-evaporate, and so it's a small cone-shaped cloud. It doesn't trail for 100 meters behind it. You'll hear the sonic boom 100 meters, but you won't hear you won't see the intense shock wave far away from the fighter jet, and that is important. This whole idea of shock waves, because a supernova generates shock waves in the material, the elements and molecules around it. The outer layers of the star are collapsing inward. The core bounces outward and creates shock waves, and those are where the elements heavier than iron-56 are manufactured, which we talked about last time. Another thing that happens is that core collapse will either leave behind a neutron star, or if it's really massive, a black hole. And we're going to be talking about black holes today in a few minutes, a deluxe lecture that you won't hear anywhere else, but we'll talk about it. But I want to go over a few more neutron star concepts with you. This is a famous formation. It's called the Vela Supernova Remnant. And that's an optical image. I don't know if that's taken with the Hubble or an amateur astronomer. It's a southern hemisphere constellation. So if you go down to Argentina or something, you'll see it easily. You know, down to Brazil, Rio, stuff like that, you'll see it easily. It's harder to see from up here. In that supernova remnant, right about here, is a pulsar. And we could see it in radio frequency, and we could see it in X-rays, and it's called the Vela Pulsar. All right? And the Vela Pulsar, right in there, we've got some really, really good high-definition X-ray images of it. And let me just show that to you. This is an up-close image of the Vela Pulsar. And this whole picture is maybe 2 or 3 light years across. So it's bigger than the solar system right now. But it's in terms of that big nebula, the Vela supernova remnant, it's pretty small. You can't really see it more than a dot on that previous image. All right, now right here, right about there, is the supernova remnant, the neutron star, and we know it's a neutron star. We can observe its electromagnetic pulse. The frequency is less than about 11 times per second. So you're going to have a study page tonight, or maybe tomorrow, on pulsars and black holes, and on that study page is a link to a really cool page out in California, Caltech, I think, and they've translated the electromagnetic pulse of the Vela pulsar, 11 cycles per second, into an audio signal. All right? And that's what your earbuds do. I mean, they have an electrical signal going up to the earbud, and then they drive a little teeny microphone or a little teeny speaker in your earbud, and that's what you hear. And the same thing with these this page. And you can hear it. It's a click. It clicks. It's 11 times a second. It's not really fast enough to be heard as an audio, as a note. You hear it as a click, a series of clicks, really fast clicks. But some of them seem like a musical note. Okay, some of the other, there's 4 or 5 other pulsars. You'll see that when I release that page. Try to make a sketch of this. Here's these 2 circular structures here. Excuse me. Those are shock waves. All right. So the exotic nuclear fusion reactions, where the rest of the periodic table is made, yeah, there's a good part of it there. All right. There are 2 jets, what we call neutron star jets, sending charged particles in 2 directions. This one, you can see this kind of cone-shaped structure back here. Looks kind of like a wedge. Okay? This is a false color X-ray. So everything here is really high energy, very hot, emitting X-rays. This one is aimed back in that direction. The other jet, you can see it up there in the upper right. Here it is. All right? Now, a couple things I want to point out to you about this. If you go ahead and make a sketch, the location of the neutron star, 2 kind of circular arcs that are the shocks. And then the directions of the jets. You can definitely do that. This jet here, it looks a little kind of almost feathery, like a cirrus cloud. We've got NASA has made movies of that. They'll observe it for like several thousand seconds, and then they'll wait a couple days, couple months, and they'll take another snapshot. They'll aim their camera for another 40,000 seconds, and then record that image. And what they've done is put together a movie. We can see that, this is just a snapshot. And tonight, when you look at that study page, you'll see a movie, and it actually looks kind of scary, actually. Like, it's because it's enormous. This jet up here, from the neutron star here out to about here, that's about a light year. So it's this enormous structure, enormous to us, but astronomically pretty small. Light year is still pretty small for like for a galaxy and stuff. But yeah, up here in this jet, periodic table factory. Everything in here, all this hot stuff that's bright blue, yeah, periodic table. Above iron 56, yep. They're making all kinds of stuff in there. Now, another spec that I want to go over with you can add this. The particles in the jet are moving in the same direction as the neutron star itself. So the neutron star, where the white arrow is pointing to, that is also moving in the exact same direction. And it may give rise to a question in your mind, Dr. B, why is that important? It's important because the jets here are not symmetric. I mean, they're both in opposite directions, so they have that symmetry. But this one down here, this one with the cone-shaped structure, is stronger. And the one up here is not as strong. And it's putting out a lot, but it's not as strong. And for that reason, it acts like a rocket motor. And when you turn on a rocket motor, whether it's a bottle rocket or a Saturn V moon rocket, you burn something, and the combustion products go in one direction, and your rocket goes in the other direction. That's how they work. Action and reaction. Well, same thing here. This neutron star had a little bit of imbalance. The South Pole down here had a little bit more than the North Pole up here, and away it goes in the direction of the North Pole, their North Pole, this particular direction. So this is like the NASA scientists said this is a little bit like a rocket motor. Okay, more reaction in this lower jet, less reaction up here. Bing. And simply because the star is not perfectly symmetric. It might have been spinning. It might have had a slightly perturbed density distribution, and it resulted in. And this thing is really moving. Another thing, the particles in this jet up here, this feathery jet, those particles are going at about 70% of the speed of light. Now, we can't do that with more than a few protons at a time. Protons, these big atom smashers over in Chicago and over in Geneva, Switzerland, we can get protons and electrons and stuff up to 99.999% of the speed of light. Really close to the speed of light. But not this much material. Right? For us to see this, even in X-rays, at this distance, for this size, it's over a light year, that's a lot of material. And this thing's got it going at 70% of the speed of light. So there's a lot of kinetic energy in this. More kinetic energy going out this direction to the lower left, and less kinetic energy going up there. But up here it's pretty good. 70% of the speed of light, they figure. Another thing I want to mention to you, and you can add this in, it's not really part of the diagram, but they can calculate the proximate density of this neutron star, various ways. All right, and the density, go ahead and write down that number, 1.3 times 10 to the 17 kilograms per cubic meter. Now that may not make much sense to you, but does this make sense? The density of water is 1 times 10 to the 3 kilograms per cubic meter. 1,000 kilograms per cubic meter. So what that means is my lectern up here that I'm, this desk up here, it's maybe close to 1.5 or 2 cubic meters in volume. So if we had a container just this size, that'd be close to 2,000 kilograms, 2 metric tons. So somewhere between 1,000 and 2,000 metric tons if it was filled with water. The water is pretty dense, but neutron stars, they are mighty dense. And matter of fact, it's 100 trillion times more dense than water. Now, a white dwarf is really dense too, because that's a collapsed star. A neutron star is even more dense. You're down at nuclear densities to the point where the neutron, something called neutron degeneracy pressure, is what holds it up against gravitational collapse. So it stops there, neutron degeneracy pressure. It's a quantum mechanics effect. And basically it says that you can't cram too many electrons into one space. But it is possible to exceed that, and when it does exceed that density, then you get a black hole. Now this one, the size of it is approximately 20 kilometers. So what we're seeing, we're not really seeing the neutron star. We know the location of it, but it's 20 kilometers away, and that is it's 20 kilometers wide, but it's many, many light years away. Okay, I think it's about 1,000 light years. All right, so we can't really see that. We can see all the hot hydrogen and carbon smithereens from the explosion that are so hot they emit X-rays. That's what we're looking at in this image. But the neutron star itself, as I've mentioned before, is pretty small. It would definitely fit nicely into Orange County. Now here's a Google map image of Orange County. All right, and we're up here. I don't know where we are. Right about here, I guess. Maybe this is UCF right here. Because this is Seminole County up here, so this is UCF right about here. All right, so what I'm going to do is draw a 20 kilometer wide circle around UCF. All right, and that's the footprint of a neutron star of the size that about what we think the Vela Pulsar is. There's the picture. All right, doesn't even stretch to downtown Orlando. I mean, it doesn't even go to Sanford. Here's the Oviedo Mall up here. This is Oviedo. There's the mall right there. Here's Waterford Lakes. Bithlo, I guess that's out here. And so on and so forth. Azalea Park, Aloma. I don't know what this road is here, but that must be... no, that's not Semron. That's... no, maybe that is Semron Boulevard. So this is maybe this is 436 here. Here's the flyover. So that's 436. So it goes out to about 436. Semron Boulevard. It's unbelievable. All right, so definitely it'll fit inside Orange County. So neutron star, very dense, very compact. And see, the thing is, That's about a little bit more than the mass of the sun right now. But it's collapsed inside that circle, a sphere that fits inside that circle. It's kind of awesome when you think about it. Here's another supernova remnant. Go ahead and make a note of this one. M1, Messier object number 1, the Crab Nebula. We've talked about it. It's in the constellation Taurus. And this is one that we think blew about 1,000 years ago. Let me park it over here to the side. This is a combo image, infrared, optical, and there's actually an X-ray image of the pulsar at the middle of this one, and it's clad with X-ray emitting dust and gas. All right, and here's what it looks like. All right, now there's the bulk picture of the Crab Nebula. Now here, to the same scale approximately, is the X-ray emitting region at the core. All right, there it is. All right, and you can see how big it is. Now that's obscuring part of the Crab Nebula, so let me move that over to the side. There's the X-ray image. All right, and I just blew it up a little bit more. So we can see that with our X-ray telescopes. And you can see a jet over here kind of curving downward. So that thing's wobbling a little bit probably. You know, the Vela Pulsar they think is wobbling. So there's a lot to learn. And there's going to be a nice combo study page, black holes and pulsars, in web courses. It's halfway done. I'll probably finish it tonight. So I'll put a little blurb in there and you'll be able to look at it. Just check out some of the images, the movies, the blurbs on black holes and stuff, and also pulsars. So let's get to black holes. All right, get your clicker out and let's do a question together. We're on frequency DD, and those of you in the back, you're clicking at your own risk. But here, I'm going to give you a question, and it's more in the way of a survey question. So just answer to the best of your preference, whatever you think is a good answer, because that's what I'm asking for. Which is your favorite black hole concept? So go ahead and read that. Okay, you have 4 options. And I'm interested to see what you guys vote for.
Does it come up as a short answer?
Yeah, this is a short answer, so... Oh, hit the refresh key if you haven't already. And revote. And hit the send key. Sorry, I gotta start remembering to do that. Don't type in DABC. Whoever did that, I can see what you... Just give me one. There you go. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, go ahead and show this, please. Thank you, Courtney. Now, I marked them all green, so everybody gets the right answer, or gets correct, because it's a survey question. And let's see, it looks like a bunch of you guys voted for D. Nobody voted for, there's no majority here, so we'd have to have a runoff between A and D, I guess. Okay, switch back to laptop. Now, the thing about it is, A, a black hole sucks everything around it. D, if you dive into a black hole, you come out in another part of the universe. These are all of them are wrong. They're all misconceptions. And this one of you, diving into a black hole, you come out in some other universe, and suddenly there's your girlfriend from back when it's all this romance stuff. That's nice in Hollywood, in movies and stuff like that, or Captain Kirk has to be rescued or something like that. But it's BS. But what you're going to be learning today is on the money, all right? And let's start talking about it. Here's another question. Hopefully this will be easy. Multiple choice, question number 2. How far does a photon of light move in 1 second? Because when you're talking about black holes, you got to talk about photons and what photons do. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ching. One. You guys did good. You crushed it, 70%. 1 light second. A few of you. Who voted for E? One person voted for D. A light year. No, that's the distance it goes in 1 year. All right. Now, I bring this up because I want to work on a special kind of a diagram with you. So clear a page in your notebook, or however it is that you take notes, and let's make a diagram. Now, this is going to be called, or this is what we call a space-time diagram. So draw a vertical and horizontal axis, and I want you to make your vertical axis the time axis. And customarily in relativity, that's what we do. We make the time axis the vertical axis. And then your other axis, your horizontal, make that the x-axis. And we'll measure the distance on that axis in light seconds. And on the vertical axis, we'll measure the time in seconds. All right? Now, there's a reason that we're doing that. And it's because we want to focus on what photons do. So this is a space-time diagram. And the reason we call it a space-time diagram is because Albert Einstein's insight, his concept was that we don't live in a 3-dimensional universe, we live in a 4-dimensional universe. And that time is the 4th dimension. And if it's a dimension, it should be treated similarly to how we treat the spatial dimensions. X-axis, left and right. Y-axis, up and down. Z-axis, toward and away. Right, those are the 3 spatial axes. And Einstein says, treat time like a dimension as well. And that's what we're doing here. All right, so this is not an X. It looks like an XY graph paper, but it's a time X graph paper. All right, now go ahead, go up about a third, and let's put in 1 second on the vertical scale. Now I want you to leave some space above that for a couple other, for the 2 second and the 1 second mark. We'll get to those in a minute. Now a photon will travel in 1 second. It'll travel 1 light second. So go ahead and put in the 1 light second line vertically corresponding to that distance on the x-axis. And put a dot right there, and I put a red one, a nice H-alpha colored red dot. That's the location of a photon after 1 second of travel from the start here. So down here at 0, 0, I don't know, put a little star or just the word origin. Okay, a photon that starts there, so you blaze your H-alpha colored laser off to the right in this direction, and 1 second later, it's 1 light second away. All right, let's do 2 seconds. All right, so go up here, try to make them as equal as you can. So So notebook paper lines work really nicely. Just kind of eyeball it in. And I measured really carefully, so this is a well-measured diagram on the screen. And so in 2 seconds, that same photon, it'll have traveled 2 light seconds. So put a dot at 2 seconds upward, 2 light seconds to the right. And hopefully, this is starting to get boring. I hope. Yeah. And because photons are fairly simple in this kind of a diagram. Go up to 3 seconds. Ching. 3 light seconds over. Ching. Put a dot out there. Cha-ching. Yeah. Now, if you'll look at my animation, I'm about to draw in the general relationship. So take a look at the screen. In general, the photon is going to be somewhere on let me burn it in there. Somewhere on this diagonal, 45 degrees. If you have seconds vertically and light seconds horizontally, then a photon, other stuff that doesn't travel at the speed of light, no. But if it's traveling at the speed of light, and all photons do, no matter, what the state of motion of the laser beam, moving towards you or moving away from you, the photons actually go at the speed of light. And so therefore, they're going to be somewhere on that dashed line. Now, we have 3 dots, for the 3 easy points, but, if it's going to be somewhere along that line at any of the intermediate times. All right, now, an alternate. And you decide what you want to do, if you want to add this to your diagram or list it over the side. You could put in the coordinates. 1 light seconds, comma 1 second. 2 light seconds, comma 2 seconds. And for the third dot, 3 light seconds, comma 3 seconds. Yeah, that's good. And you can write it that way. Depending on what you want to do. All right. Now, the important thing is that in this scale, on a space-time diagram with these distance scales and time scales, the path of a light beam is always going to follow a 45-degree line. Now, this is the 45-degree line heading off to the right, and we're going to draw one here in a second. Off to the left. But in general, especially when you're trying to understand black holes, the light path in space-time, and this is a simple example of it, is really important. So let's take a look and let's go to the left now. Here's my rightward pointing photon path, starting down here at the origin. Now let's say that you beam your, at the same time, same location, you beam your H-alpha red laser the other direction. All right, that's going to go out along this 45-degree line. All right? No problema. All right? So if you're trying to signal to someone, off to the left, if you're trying to send dots and dashes or zeros and ones on the internet using a laser beam off to somewhere over here in the art gallery or somewhere over there over by the student union, by the student union, you'd be on either one or the other of those photon trajectories. Now, I want you to draw in another trajectory in space-time for something that's not a photon. So here's something, you give it a kick off to the left, and it's not traveling. It doesn't have the same tilt angle, so it's not a photon. But you could, it's like you throw a water balloon. Somebody's over there, you want to grease them with a water balloon. All right, you throw it to the left. And so this is a leftward one. And I made this one fairly close to the same tilt. It's above the photon line, but it's fairly tilted. So that's like maybe 50-something degrees. I forget exactly what the angle there is, but it's above 45. Now let's do one on the right. Here's something, you throw a pencil in that direction, or I throw a Nerf ball over to, what is your name again? No. Yeah. Allison. If I throw a Nerf ball over to Allison here at the command post in the front row, that's like the black track here. So different tilt angle. And make this one a little bit steeper. Okay? Now I'm going to ask you an IQ question here in a second, so make sure you have a good sketch of this. All right? Question, and this is multiple choice question number 3. All right, same diagram. Which object is moving faster? Ooh. Think. What does it mean in this diagram to go fast and slow? Time progresses upwards. And if position changes to the left or to the right, you're on a straight line of some kind. Go ahead and talk with your neighbors. Talk it over. If you have a neighbor, if you're not sitting by yourself, because talking helps you think. I see a lot of people going like this. It's good. You're thinking with your hands. It's good. Love it. All right, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh my goodness. You guys are geniuses. A lot of you know what? The morning class got caught napping. Yeah, go ahead and make a note to yourself in a space-time diagram. The tilt of the line, the path, corresponds to the speed. Either leftward speed or rightward speed. All right? The closer you are to 45, the faster. All right? Now, here's an example of something at rest. Oh my goodness. This diagram's off the bottom. Sorry about that, you guys. Anyways, you can almost see the bottom down here. Down here. If you are at the origin at time t equals 0, at x equals 0, if you stay there, your path through space-time is right on the time axis. The position of the observer is on his time axis. And that, my wonderful students, is everything about relativity. The position of the observer is on his time axis. Now, here's Einstein's theory of relativity. What if your friend is on this trajectory? Where's his time axis? His time axis is over there on that tilted line. And your time axis is over here, and that is where all the weird paradoxes you may have heard about with relativity arise. Your time and your distance measurements disagree when you measure the same event. And it's because of the basically treating time as a dimension. All right, now, another thing I want to point out, Kayla, do you have a question? My answer to that is no. Because if you were going faster than the speed of light, you'd be over here to the right or over here in this grayed out area to the left. So go ahead and shade below the 45-degree lines and just write in the word no. Because in Einstein's theory of relativity, nothing can travel faster than the speed of light. And the speed of light is a constant. So even if you're in a rocket ship going 50% of the speed of light and you shine a laser beam out the front of your rocket ship, that laser beam is not, the photons are not moving at 1.5 times the speed of light. They're still moving at the speed of light. They're just blue shifted. If you shine a red H alpha laser out the back end of that same spaceship, it's not going to be going, the photons are not going to be going 0.5 the speed of light. They're going to be going the speed of light. They're going to be redshifted. That's what happens. They don't slow down. They redshift or they blue shift. So that being the case, you cannot go faster than the speed of light. There's stuff over here that does not belong to you. You cannot go from the origin, which unfortunately is off the bottom of the screen here. You can't go from the origin out into this gray area, Kayla, because we don't, in Einstein's theory of relativity, going faster than the speed. And I don't care what they say in the movies about going faster than the speed of light. Do not get me started. Anyways, Zemansky, question. Was it about that, going faster than the speed of light?
Well, you mentioned the spaceship, and there's been a lot of paradoxes about a spaceship going at the speed of light.
Right. Well, that was Einstein's famous thought experiment. That's how he developed the theory. He said, what if you had, and it was 115 years ago that he was thinking about this. So they didn't have rockets, they didn't have jets, they didn't have airplanes. Well, maybe they had it. They had the Orville and Wilbur Wright had, the flyer out there at Kitty Hawk. But so he was thinking in terms of streetcars in Vienna, or streetcars in Geneva, I guess, maybe where he was living. And he said, what if my streetcar is going at the speed of light? And I shine a flashlight in the forward direction. What will the observer on the sidewalk see that's at rest with respect to my streetcar? And the answer is, he'll see a redshift. What Einstein proved had to be the case was that the observer would see the photon going at the speed of light, but it would be redshifted or blue shifted. Depending if it was coming towards the observer on the sidewalk or away. Just like just like that Doppler shift that we heard with the freight trains. That's what Einstein was thinking about. So yeah, that is the essential thought experiment that you brought up, and that's the same one that Einstein started with. All right. Now, here's this diagram again, and this is a little bit better. It's raised up. The inside of these two dashed lines, the two photon lines, that is called your causal future. You cannot do any causal connection between you here and anything out here in the no-go zone, the gray zone left, the gray zone right. You can beam a photon to events up here, way out. You can get stuff out to the left, but it's going to take time. Right? So you can go all the way out here to the left, but it's going to be way up on the time axis, all right, with a photon. And it's going to be even further up on the photon if you use this water balloon to try to affect something. All right, so if you want to beam somebody with a laser beam that's far away, yeah, you could do it. It's going to be up here about this much time. If you want to do it with a water balloon, the blue line, even more time, because it goes more slowly. You can't, if you're trying to beam somebody out here at this short time interval, can't do it. All right. So this is how space-time has what we call almost like a confinement of causality. All right. So your causal future is inside this cone. And so causality exists for us relative to this point. Now, somebody else in another galaxy, their origin might be over here to the right. Okay, eventually you'll be able to communicate, but it'll take time. And you won't, if they're right here, you'll not be able to connect. They won't either, anything down here. But eventually, the 45-degree line from over here would intersect your 45-degree line, and then after that, you can have a conversation. Question over here.
I was actually about to ask someone that maybe there's something that's out of our grasp that could reach past into that nebula area.
Yeah, you can. This is your causal future. This particular event, you at this position at this time. All right, now, if you go somewhere out here on this black line here, they're going to have you draw in a new light cone. Put a dot and then draw a new light cone. Okay, I'm jumping ahead of myself. This 45, left and right 45. Once you go into two spatial dimensions, we call it a light cone. All right, so there's your light cone. All right. And the light cone is like the HR diagram of relativity. It's the tool that every person that studies black holes, neutron stars, the Big Bang Theory, we're all thinking about, among other things, light cones and what they do. All right, so if you think about it, if now instead of just having left and right and then the temporal axis going straight up, if you now have forward and back, and then the time axis, then you get a cone. All right, so this is what we call a light cone. Here's another picture. Maybe you can draw in perspective the light cone. And so here's another one. So this would be your future light cone up here. Here's you. Here's the origin. And here's your past light cone. There's one, I didn't draw it in, but that would be called the past light cone. That's your causal past. You can be affected at this time in your history, you can be affected by every event that happened inside this light cone. But outside that light cone, stuff over here to the left or to the right or anywhere around it, you can't. All right. Now, let's go back and do another multiple choice clicker question. And let's see if you guys are thinking. See if you can think on your feet. All right, graph paper. Seconds vertically, light seconds horizontally. Go ahead and vote. You know what I did in the first class? I forgot to animate it. So this is the first. This is where it started. 10 seconds to vote. 10, 9, 8, 7, 6. Because I just gave you this answer about 90 times in the past 5 minutes. 4, 3, 2, 1. Zero. I was distracted by a guy up here in the front. He's going like this and stuff with his hands.
I was explaining.
Yeah, it's good.
Half of
Yeah, it's good. It's good. It's good. Yeah. Geniuses. 95% of you got it right. Yeah, 45. So you're either, tilted to the right 45 or tilted to the left. But if you think, if you're thinking in two dimensions, then you got a full cone, a 45-degree cone, kind of like a snow cone. So here's the other side. And here's another way to look at it. Everything inside the cone is slower than c, the speed of light. And in fact, stuff that goes straight up the time axis, which would be this line right here on this diagram, there's the time axis where my cursor is, that is stationary. So go ahead and make a note. The time axis marks the position of a stationary object. And in fact, it's your position. You're the observer. You with a wristwatch and you with a meter stick. All right, now this one's a little trickier. I want you to think carefully about this one. It's a geometry question. Two photons. You aim them out at perfect 60-degree angle. How far will they be apart? In other words, the yellow question mark, what's that distance? I want you to think. Do you remember your high school equilateral triangles? You remember that? So go ahead and vote in, think, consult with your neighbor, use your hands to think with, See, everybody's pointing at the diagram now. Yeah. Is it possible for what? Photons always go at the speed of light. Uh, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. The three locations form an equilateral triangle. Okay. If that's the case, then this is the correct answer. And 90% of you did get that, so good. Now, let's start putting all these concepts together. I'm kind of working you through these mental IQ tests. Let's put it all together. Let's make an outline. Okay? Now, we know that photons normally travel along straight lines. If you're in the lab here on planet Earth, you're nowhere near a black hole or a neutron star or anything like that. Photons travel, and 1 light second for every second of travel. All right? So that's normal. Now, if you do have some curvature of space-time, if you're near a black hole, event horizon, or you're getting close to a neutron star, you're going to get significant curvature there too. And even the sun has a little bit of curvature of space-time that we can measure the effects. Okay, so things might start looking a little bit different. Now, to understand it, we're going to talk about a 1 nanosecond burst of photons. So in one nanosecond, 1 times 10 to the minus 9 seconds, a photon will travel 30 centimeters. That's about 12 inches. All right? So if you have a laser and you buzz your laser for 1 nanosecond, which you can't do, but we can do it electronically for sure. A 1 nanosecond pulse in a laser is about 12 inches long. And so you have a wave packet of photons heading out, and it, it forms a packet of about 12 inches. And if you do it in all directions, it would form a wave front or a shock front. Okay, so shock wave about 12 inches thick. Now I'm going to give you a picture of that. So let's think of, you using an H-alpha flavored laser, and here's your source over here, this yellow disk, and let's say you blaze out a 1 nanosecond pulse. Now take a look at this. This is what it's going to look like. Zing. All right? And this thickness here is about 12 inches. All right? So no matter how far out it is, it's going to be about 12 inches from the first photon to the last photon that you blaze out in 1 nanosecond. Now the thing about it is, you blaze out a finite number of photons, so the further out that shock front goes, the more dilute the photons will be. They won't be, they'll be intense if you're down here close, down here. But out here, there's still going to be 12 inches thickness, but there might not be so many of them in that 12 inches. It just depends on the distance. All right? Now, so here's the kicker. In flat space-time, every second that 12-inch shock wave travels another 1 light second away from the origin, and it spreads out. You would say that the photons are diverging from each other. Go ahead and write that down. The photons diverge. And and distance-wise, they're going to be going, 1 light second for every second of travel. So, no problem. And eventually, they'll be so faint you can't really see them. But if you're in fairly close, you'll be able to see a good dense bindle of H-alpha red photons. All right. So this idea that the shock wave goes outward from the origin, spreading out, is good. It's lovely. 1 nanosecond flash of red H-alpha. So if you have a circular or a spherical array of lasers pointing outwards, and you blaze all of them for a nanosecond at the same time, that shock wave of red H-alpha photons, always 12 inches across in thickness, and always 1 light second away from the origin, and always spreading out, unless you are near the event horizon of a black hole. So make a note of that. In flat space-time, in the lab, here where we don't have a lot of curvature, they diverge, no problem, everything's hunky-dory. But if you're near some space-time curvature, black hole event horizon, neutron star, even the surface of the sun, you can catch some unconventional behavior. So let's take a look at the black hole event horizon. Now this is going to be this will be the last few minutes of class. We'll probably dismiss a couple minutes early today. Now we know that the mass left over from a supernova collapse will either be a neutron star or possibly it'll collapse down to zero volume. That'll be a black hole. And so we think, for something that's maybe 3 times the mass of the sun, you might be getting a black hole out of that instead of a neutron star. And so the neutron degeneracy pressure that supports a neutron star against gravitational collapse, if you have enough mass, it's not going to support it. Gravity will be too strong, and it'll smush everything down to zero volume. Now, in other words, you get a black hole. Now, here's two common descriptions of a black hole. One, nothing even light, not even light, can escape from a black hole. Right? Emphasize the word escape. And let me add to that, emphasize the phrase escape velocity. Now, some of you know that escape velocity for the surface of the Earth, it's pretty fast. For us to get even 3 men in a space capsule to the moon, we have to attain escape velocity from the surface of the Earth. We've got to be able to get past Earth's gravitational pull, and so the escape velocity, it's pretty fast. So we need really big rocket engines. You know that the Apollo space capsule was not very big, way smaller than the space shuttle. But we don't lob we're not trying to get the space shuttle up to the moon. If we wanted to get the space shuttle up to the moon, you know, like they do in the movies, you know, like with Bruce Willis and stuff when they're trying to save the Earth and whatnot, we don't have anything near rockets that big. Sorry. You know, we could barely get a space capsule or a little teeny satellite to orbit the moon. But anyways, escape velocity, yeah, that's a thing. And you can compute, you know, do a little bit of trig and a little bit of calculus and figure out, you know, for the certain mass, certain radius, what the escape velocity is. And, you get a certain figure. And once that figure is greater than the speed of light, 3 times 10 to the 8 meters per second, bing, you've got a black hole. All right, so escape velocity greater than the speed of light is one common description for black holes. The other way to describe it, the event horizon marks the point of no return. If you cross the event horizon, you're done. You're not going to escape. There's the only inevitable point in your future is the smoosh down at the center of the black holes. You're going to get smooshed down to zero volume. And as you go into the black hole event horizon, you're going to get pulled into pieces, you're going to get elongated and squished into spaghetti. So it's, you don't want to try that either. You can talk about it, but it's not going to be practical for humans. There's other ways to describe a black hole. Number 3, those are the common everyday things that you hear. And these ones are righteous. That first clicker question we had was misconceptions. All right, these are not. Now, what we're going to try to do is get a geometric description of a black hole in terms of what photons do. All right? So we're going to get a geometric description of what photons do in the space-time near a black hole compared to space-time here on the surface of the Earth in a lab where it's flat, there's no curvature. The other way that you can do it, and I'll allude to this on Thursday, is entropy. The information, the amount of information that you can send and receive. Now, this is the thing that Stephen Hawking thinks about a lot, and a lot of us nerdballs in relativity think about the information content in a space-time near a black hole and inside a black hole and stuff. So I'll give you a little bit of a blurb on that on Thursday. And it's both of those are righteous, and they're related to what photons do. So we're going to, so we're not, 3c here, escape velocity, that's something that you can compare to rockets and NASA launching stuff, and it's nice. But geometrically and entropically, we want to think about photons. So let's talk about a shell of photons for a few minutes, and then we'll dismiss. If space-time is flat, like in this first diagram, light will go from a star up here straight to the Earth. And if it doesn't if it's not aimed at the sun, it'll go past the sun and it'll hit the earth. So if you're looking in that direction, you turn your head to that direction, you'll see that star with a telescope or with naked eye if possible. All right? Now, so in flat space-time, you got a straight line all the way to the earth. Now, if there's a region of curvature along the path, you're going to have some trouble. The photon path curves. And it's kind of weird. Let me bring the sun up there. All right, so let's say that the sun is in this position. Now, that photon is not going to get to you on the planet Earth. It's going to be blocked by the sun. All right, but other photon paths will curve as if they're responding to gravity. If you send a space capsule past the sun or past the Earth or past Jupiter, it'll curve around. It'll get slingshotted past Jupiter. We do all that all the time with our probes that we send to the outer solar system. But photons don't have any mass. But Einstein said, yeah, they should still respond to curvature of space-time. And so people set out, how are we going to ever measure that? And he said, well, look, see if you can find a total eclipse of the sun and then see if light will bend around the sun and allow you to see a star that's actually behind the sun, but because of bending of light, you can see it. And that's what I'm going to show you right now. So this star right now is behind the sun. You should not be able to see it. And this photon that I've got mapped out with the dashed line, you won't be able to see it. But this photon, it's curved. It's on a slightly curved path. It starts out as if it's going to go past the Earth. It's going to whiz right on by. You won't see it. But because it grazes right near the sun, it'll curve, it'll bend, just like a spacecraft going past the moon. It'll bend, it'll slingshot past Jupiter. That's what happens with a photon, even though it doesn't have mass. And so now, this is what we call deflection of starlight, and they observed it. They went down to Africa, an island off the coast of Africa, in 1919, where there was going to be and I think some guys went over to Brazil or something, and they knew there was going to be a total eclipse, and they looked for stars that they shouldn't be able to see, and by God, they found them. They saw them. They saw some stars that this is behind the sun. We shouldn't be able to see it. But because the sun curves space-time just a tiny bit, they could see it. All right? And that was the first verification. Now, so you don't get this photon, you do get this one, and look, here's where the star appears to be. Star appears to be way over there. So the star is actually behind the sun, but you see the photon coming in from that direction. So it's like, okay, the sun is over here, the star's directly behind it, I shouldn't be able to see it, but actually if I tilt my head a little bit to the side, I actually do see it. So and this is what we call gravitational lensing. Now, gravitational lensing is what we need to understand what photons do near the event horizon of a black hole. So now, last few minutes here, this is the important part. Don't get up at... Right, so here's what I want you to do. Think of a series of blue flash bulbs. And let's say that they all go off for 1 nanosecond. So you get a good 12-inch thick shock wave, and let's call them red. H alpha red. And in a regular flat space-time, they're just going to, they're going to go out along these paths. And they're going to diverge in the sphere. Now, this is a sphere, so we're thinking about a sphere. The sphere is getting larger. So r, the area is getting larger, 4 pi r squared, because r is getting bigger. 1 light second bigger for every second of travel. And so so go ahead and make a note of this. In flat space-time, you get more divergence per second, because they're getting further and further apart. If they were 60 degrees apart, that's why we did that little exercise. How far are they apart in 2 seconds? Well, they're 2 light seconds apart if they're aimed. Now these ones aren't aimed at 60, but they're getting further and further apart. We still have a 12-inch shell, and we would say that the shell is diverging. It's not converging at all. But now, if you have the same set of flash bulbs around the event horizon of a black hole, completely different. First, you blaze the flash bulbs for 1 nanosecond. All right, there's your wavefront. Now, in flat space-time, those are going to go out 1 light second for every second of travel time. And this is where they would like to go, but they never get to go there. They never diverge. Write that down. Because of gravitational lensing, instead they converge, and they're lensed so quickly. The curvature is so strong. Not like the sun just barely lenses stars, just a teeny bit. Fractions of a second of arc. But a black hole, it lenses so quickly, they're trapped. They don't get further apart. They're burning outwards. They're in the right direction, and it's light. They're moving, but they don't get any more area. They don't capture any more space. They're trapped. So here's the formal definition of the event horizon. It's the outermost surface of trapped photons. And that, my wonderful students, is how Stephen Hawking would define an event horizon. The surface, the outermost surface of photons that, even though they're aimed in the right direction, they're not capturing any more area. They're burning outwards, but they ain't, it's like, spinning their wheels. They want to diverge, but the curvature of space-time says, no more diverging for you. We're going to trap you. So you got this situation where you're in this MC Escher picture here, and you got a lot of troubles at the event horizon. Now, on Thursday, we're going to talk about spherical coordinates, and we're going to talk a little bit more about black holes. Oh, by the way, hold on. Don't leave the room. Thursday, we're going to have a special iClicker review session that's going to be converted into bonus points. I mentioned it last time, so don't miss class on Thursday. You get some bonus points. All right, you're dismissed. Yeah, I'm going to give you, it's going to be like on exams. So, we're going to have a final lecture, and then the last 20 minutes will be for the review session.
Okay.
And I'll give you a 1-page handout, 15, 20 questions maybe, multiple choice, and maybe a calculation.
Okay.
And you'll click them in with your clicker the way that we do at the end of a test, Except now you'll have 15 or 20 of them. And you can study with your neighbor and, talk it over and just, So it'll be like a little mini review session and stuff. And then your score, I'll convert that into bonus points, maybe 3 or 4 bonus points.
All right, thank you. And they'll be free for us to keep at the...
Yeah, and then you'll be able to keep the handout, so it'll be kind of like a mini review guide.
Okay.
Okay?
All right, thank you.
So, you are welcome. All right, let me get my... Here we go.